Hi guys, we'll be starting shortly. Since people are joining, let us wait for 5 more minutes. As you all know, today is our third session. Hi guys, we'll be starting shortly. Since people are joining, let us wait for 5 more minutes. As you all know, today is our third session. Hi guys, we'll be starting shortly. Since people are joining, yeah, right. So today is our third session, and we'll be covering some more popular machine learning models, and we'll be focusing more on the classification use cases of machine learning. Some more popular machine learning models, and we'll be focusing more on the classification use cases. And as already Karthik has mentioned, today's attendance will be taken through QR code. We'll be showing a QR code 2 to 3 times throughout the session, so that even if you miss once, you can scan it again. You need not scan all the 3 times, and also we won't be taking responses more than once, since we have kept the limit as response, you can respond only once. Okay. So even if you miss to scan the QR code for the first time, you can scan it either the second time or the third time. And this is applicable not only for the YouTube, the people who are attending the session through YouTube, but also for the people who are attending it on MS Teams. Initially, MS Teams people were allowed weren't asked to scan the QR code, and they weren't asked to fill the G form. But from now on, everyone will be asked to fill the G form, and that will be a policy same for whether you are attending it on MS Teams or whether you are attending the session on the YouTube live stream. So please don't send out messages again on the WhatsApp groups asking for the Google form link. We'll not be doing that. In order to ensure that no one misses out on the G form, we'll be showing the QR code 2 to 3 times. So please refrain from sending out messages again and again, because we'll not be doing that. We want to ensure that only the people who are attending the session will be able to get access of the QR code and not the rest. I guess that's all. We'll wait for 2 more minutes and we'll be starting at 5:05. Yeah, thank you. Also, a few of you were requesting or they were asking doubts about the assignments. So what we mean by assignments is basically the tasks. So we have already shared the GitHub link on all the WhatsApp groups and even on the announcement group. You can check it out there. So if you open the GitHub page, you'll be able to see the tasks that you have. So up to now, we have uploaded only task 1, and the deadline for it is 15th July. So even if you are unable to attend all the sessions, you can compensate it by making sure that you attempt and make submissions for the tasks that we are sharing it with you guys. Okay. And also, apart from that, after every session, we are sharing a small mini quiz on all the groups. We are circulating a G form for the same. So do attempt those as well. That will help you to get a better understanding of whatever has been covered in the session. And also definitely feel free to ask whatever doubts you have, whether it is related to the task or whether it is related to the session or to the mini quiz or whatever. We'll feel free to ask your doubts. We'll be there to help you out. I guess we can begin now. Yeah, Rishi, you can start.
Yeah, cool.
Also, one more small announcement. Yeah, so for the Q&A, for ensuring that your doubts get clarified during the session, we'll be following the same procedure. That is, we'll be sharing with you the Slido link, and also, yeah, we have already posted it in the WhatsApp groups. Even Rishi will be showing the QR code for the Slido Q&A page. So whatever doubts you have during the session, feel free to post there. The coordinators will be handling those. Rishi and Anupam, both of them will be taking up the doubts. And Also feel free to raise your hands. We'll be giving you the mic access so that you can unmute and speak. Yeah, Kishore, do you have any doubt? All right. Okay, Rishi, you can start.
Yes, okay. So, hi guys, I'm Rishi. I'm a coordinator in the AI Club, and today I'm going to be talking about support vector machines. So, before we get into the presentation, this is the QR code for the Q&A. I'll leave this for a few seconds so that you guys can scan this. All right, okay. So, let's get started with the session. So support vector machines, right? So what exactly is an SVM or support vector machine? So I think if you've attended the previous sessions, you should be pretty familiar with supervised learning. And this is basically a supervised learning algorithm. And it basically, you use this to classify for like linear and nonlinear classification, regression, and outlier detection. Now, today we'll be mainly focusing on classification. And that's actually the main use of SVMs as well, and we'll be looking into classifications of only two classes. Okay, so let's try to understand what's going on over here for a second. Okay, this is a graph, and x1 and x2 over here are two features. Okay, and we call this a feature space, and these squares and circles that you see are essentially data points. And as you know, a feature is something that we can distinguish like anything on, right? Like in this case, two classes. So every data point has some value and some feature, and essentially its location on this plane kind of describes what values it has for each feature. And these lines that you see over here are what we call hyperplanes. So when we have two classes, right, of data which we want to classify, the way we do it with SVMs is we'll create a hyperplane like you can see over here to basically distinguish those two classes, and that's the main objective of what we're going to be looking into today. So before that, a little bit of jargon, right? So there are two terms I want you to understand first: support vectors and margins. So for the time being, ignore the green line and the red line. Just focus on this white line over here, which is your hyperplane. Your green and red dots, which are your data points, right? And the way we define support vectors is the two closest data points from each class, right? Like so, the closest data point from each class. So these two in this case, to the hyperplane is essentially, those are basically your support vectors. And now we will draw two new hyperplanes which are parallel to our original hyperplane through these support vectors, and we call them your positive and negative hyperplane, right? As you can see in the diagram. And so the way you define your margin essentially is you add up the distances that each of these support vector make with the hyperplane, and that sum is essentially a margin. And a different way to think about it is if you just look at the distance between these two planes right here, your positive and negative hyperplane. So that's your margin in simple words and support vectors, right? So this line over here, it says, right, there are two types of margins, hard and soft margin. And in SVM, we consider a large margin to be a good margin. So that's what I'm going to be looking into next, is why is a large margin a good margin? And first of all, this basically means that obviously this shows you that because you can create multiple different types of margins, it means that for the same data, we can have multiple different hyperplanes which can separate your classes. And the one which has the maximum margin is what we call our optimal hyperplane. Okay. And my question right now, at least what I want to get into, is why should it be a large margin? So before that, I just want you guys to scan this. This is not a quiz to test any understanding or anything. It's a pretty obvious answer. This yellow dot is what we call is like a test data point, and I want you to predict which class this belongs to, right? So just quickly scan this barcode, and I'll open up the poll. So if you guys have scanned the barcode, I think I can activate the first poll. Mm. Yeah. So let's see. Yeah, pretty obvious. It should be green, and that is right. It's the green one. Okay. So this basically shows me that you all kind of understand also how we're really classifying, and it's this makes sense, right? It makes sense for everybody that this should be a part of the green class because it's very close to these green points and pretty far away from the red points. And as you all correctly noticed, it should be a green circle. Now, what I've done here is I've taken two different hyperplanes and notice that one of them has a very small margin and one of them has a very large margin. And they both very effectively classify your training data. If you were to ignore this point here, they classify every other point, which is your training data, very, very accurately, right? So where does the issue come with a small margin? Now, if you look at this, right, your hyperplane with a very small margin is actually incorrectly classifying this as a red point, when we all know it should actually be green. Whereas this has correctly identified it as a green point, as it lies on this side of the hyperplane. So what exactly is going on over here, and why is it that we want a large margin? Now, I've showed you that a large margin will actually end up, I mean, a small margin can cause misclassification, but let's try and understand exactly why that happens. So if I have something like this, okay, and if these are my two classes, let's say, and something here. Now, the way I'd like to describe a hyperplane with a very large margin, right, like something like this, is that it very well distinguishes the two classes, if that makes sense. As in, according to your hyperplane, these classes are pretty far apart from each other according to your hyperplane, the way your hyperplane looks at it. So it has no confusion in a sense as to like how to differentiate between the two classes because they're pretty far apart from each other, right? So they're very well separated. But now the thing is that a different hyperplane will actually separate these classes differently. For instance, a hyperplane like this, which has a very small margin compared to the previous one. Now, according to this hyperplane, both of these classes are not as distinct, right, compared to each other as it was with the previous one. And it's pretty obvious that, let's say you're very sure, right? You're very sure that something belongs to a particular class, but it's very far away from the hyperplane. Now, there is no ambiguity when it comes to a point like this. The major issue arises when you have points over here and here, something which is very close to your hyperplane, because these points could essentially lie on any side of the hyperplane, and it's very ambiguous. You can't be certain and say that this is for sure because this point for sure belongs to class B and this point for sure belongs to class A, because they're very close here. So let's say your hyperplane was slightly at a different angle, right? Like let's say something like this. Now this would completely change which classes they belong to. And that is because these points aren't very distinct, right, when it comes with respect to your hyperplane. And this is why we essentially want to create a bigger margin, is because a bigger margin can essentially distinguish your two classes much better. This does not depend on the inherent separation of the classes itself, right? But what actually matters here is how separate does the hyperplane think these two classes are. And yeah, so now that we're convinced about that, let's just look into a little bit. So if you remember, I keep calling this a hyperplane, but this is actually a line, and I'm pretty sure some people must be confused as to why I'm calling it a line. And it's actually because this is just like a name, and your dimension of the hyperplane is actually doesn't have to be 2 or even 1. It could be anything. So over here, as you can see, this is 2 dimensions, as in you have 2 features to distinguish your hyperplane on. And naturally, if you have, let's say, a piece of paper which is 2-dimensional, and if I ask you to separate this piece of paper into 2 sections, you're going to draw a line on it. And over here, you can see there are 3 features. So your classes can be distinguished on 3 parameters. So it's 3-dimensional. And naturally, in your house, if you have 2 separate sections, they're separated by a wall, which is 2-dimensional. So I think you're catching on what's going on over here. If you have n features, your feature space or input space, which is this in this case, becomes n-dimensional, and the separation boundary, which would be this over here in this case, so that would become n-1 dimensions. So for a 2-dimensional space, your separation boundary is 1-dimensional, and for a 3-dimensional space, your separation boundary is 2-dimensional. So that's basically how you decide the dimensions of your hyperplane. Now, let's look into 2 types of SVMs that we're going to be covering today, linear and non-linear. So you can define these pretty simply, and it's in the name itself. If you have data which is linearly separable, then it's linear SVM. And how do we define linearly separable data? Well, on a 2D space, because it's easy to visualize this on a laptop screen and in general, we define linear as one line, right? So if I can create my height, just one straight line, and I can separate two classes, then your data is linearly separable, simple, right? And look at this one. This is your data set B. Now over here, can I draw one straight line? Actually, you'll realize if you try as well, you can't. There is no one straight line that I can draw to perfectly separate the blue and the green class. It has to be a closed loop like this. So obviously this is going to be non-linear because you can't draw one straight line and separate them. But now I already told you that you can have multiple dimensions, right? Based on how many features you have. So what is linearly separable in the in 3 dimensions? Because that's one more thing we can visualize, right? So what a line is to a plane, if you think about it, is what what a line would be in 2 dimensions is what a plane is in 3 dimensions, right? It's the same relation. So if I have one straight plane, like you can see over here, which can separate two classes, then it's basically the equivalent of linearly separable in 3 dimensions. But let's say I have a paraboloid, right? Like a paraboloid, which is your separating boundary, then it's not linearly separable. Okay. So that is linearly separable and non-linearly separable. Now, whenever we have non-linear SVMs, we can't use the same methods as linear SVMs. So there are certain things like kernel tricks which we'll use, which we'll get into later on to classify these things. For now, let's focus on what a hard margin is. So a hard margin is basically a part of linear SVM only, and it's, I mean, the concept at least we're going to be looking at is something which is based on linear SVM. And in this case, what a hard margin tries to do is it tries to classify the training data, right? By and it basically makes sure that you don't misclassify any training data point. So it will try to find the hyperplane which correctly classifies every single data point in your training data. That's how we define a hard margin. There is no room for misclassification. So I've written 3 equations here, which basically describe your 3 planes. And the first one is what I've written to describe any point. So now, first of all, if I draw, let's say, a hyperplane like this, a random arbitrary hyperplane, and I created a vector W, which is essentially any vector which is perpendicular to your plane. Okay. And your X is basically the position vector of some data point that lies on your feature space, your input space. Now, I'm saying X dot W is equal to C would be true for any given point, any data point that lies on the decision boundary. Now, if you're not convinced about that, I can show you that this is indeed correct. So let's say we have something like this, okay? And if I have my hyperplane here, and this is your vector W, which is perpendicular to your hyperplane, right? Now, if I have some data point here, which is like what I said, on exactly lying on the hyperplane, then any vector like this, any vector X over here, I am saying that X dot W, and by the way, this is the dot product. I'm pretty sure everybody is familiar with the dot product over here. And this is equal to C. And we all know that this is also equivalent to saying XW cos theta, where theta is this angle over here, the angle between the two vectors, and X is basically mod of vector X and W is mod of vector W. Okay. And so if I were to convince you that this is true, if I now, let's say, ask you to find this distance here, right? What would you say? You know that this triangle over here is a right angle triangle. So it's obviously going to be X into cos theta, right? And X cos theta, right, is basically just C by W, because X W cos theta is equal to C. So I can write this distance as being equal to C by W. And X cos theta, in other words, is basically just the projection, right, of, or I could rather say the component of vector X that lies along vector W, right? It's the component of vector X that lies along vector W. And for any point here, any point on the hyperplane, the way I'll find my component is I'll drop a perpendicular, okay? And once I've dropped my perpendicular, I'll measure the distance from here, because the starting point of all these vectors will be here, right? So for any point, we can all agree that its component, if this point lies on the hyperplane, then for all such points, we know that its component along W vector is going to be equal to C by W. So we know for a fact that for any point on the hyperplane, this will always be true. Similarly, if I take, let's say, something like this, which is a positive sample, which lies ahead of the hyperplane, okay, and I find the component of this along the hyperplane, Okay. Now I'd say everybody can agree upon this fact that this distance over here is definitely larger than c by w, right? This distance is definitely larger than this distance over here, right? So we can say that for any point which is a positive sample, right, your x cos theta is going to be more than c by w. And that's, in other words, just saying x dot w is more than c, which is exactly what I've written over here. And the point of this exercise was just to convince you that this is how we can represent any positive samples, negative samples, and a sample that lies on the hyperplane. And this is obviously, we can extrapolate this from the previous two equations. Now, okay, so now that we've done this, let's actually try to get into a little bit more math. So we're going to get two new terms here quickly. Okay, b and y. So b is, it's nothing, it's basically just minus c. We're just doing algebraic manipulation here. So you'll notice that x dot w plus b is equal to 0, sorry, is more than 0, is essentially the same as writing x dot w is more than c, because this is minus b and you bring it on the left side. So this here is the equation of any positive sample. This here represents negative samples. The way y is defined is y will give you 1. So y for all positive samples is plus 1, and y for all negative samples is minus 1. So you can see this pictorially over here. For all red points, your y is plus 1, and for all green points, your y is minus 1. That's how we can think of y. Okay. And coming to the equation of the hyperplane, we can write this as x dot w plus b is equal to 0, because that's the same as writing x dot w is equal to c, right? Now there are two more equations I've written here which might seem slightly confusing to you, which are for L1 and L2. And I brought this up earlier. L1 and L2 are essentially your negative and positive hyperplanes. And I'd already mentioned that your hyperplanes are something which are parallel to your positive and negative hyperplanes will be parallel to your decision boundary, right? So if your overall hyperplane is of some format like this, right, like sorry, x dot w plus b is equal to 0, then any planes which are of this form, right, these are obviously parallel to they are parallel to this hyperplane, right? Has to be. Mathematically, we all know that this is correct. So now the real question is, why should your magnitudes of lambda, first, let's actually look at a case like this, okay? So this is your negative hyperplane, this is your decision boundary, and this is your positive hyperplane. And we'll call this distance d1, we call this distance d2. And obviously the margin is the distance between your negative and positive hyperplane, which will mean d1 plus d2 is essentially your margin, okay? And basically d1 minus d2 is what we're more interested in, or the equality. So I know that by symmetry, if the magnitudes of lambda 1 and lambda 2 are equal, right, then that implies that d1 and d2 will also be equal, right? And this is also very easy to prove mathematically. I don't need to do this. But essentially, if lambda 1 and lambda 2 are equal, then these distances will also be equal, right? So that's great. But the real question is, why do I want lambda 1 and lambda 2 to be equal? I mean the magnitudes. Why should d1 and d2 be equal in the first place? Why can't I take something like plus 10 and minus 8? Why does it have to be plus 7 minus 7, or plus 50 and minus 50? Why should their magnitudes be equal? Why should d1 and d2 be the same? That's the main question here. So let's look at what happens if we don't keep it the same, right? So we have, let's say, two classes here. And what I'm going to do is I'm going to show you how two hyperplanes perform, right? One hyperplane which has a very small margin with one class and a very large margin with the other, and another hyperplane which is dead center between the two support vectors. Okay, so let's look at a hyperplane like this. Now this will be your negative hyperplane, this will be your positive hyperplane, and if I, let's say, add a new data point, right, somewhere over here, right? Now all logic will tell you that ideally it should belong to this class, right? It makes sense. It's very visually obvious, and logically this is what you're going to predict, and you'll be right in predicting that. What goes wrong is your hyperplane, because your hyperplane says it lies on this side of the hyperplane, so it must be a triangle, and that is clearly just wrong. That's wrong. But then the real question is, what is to blame, right? Why is, and what could fix this error? So now let's think for a second. So this hyperplane, which you see creates a very small margin with one class and a very large margin with one class, is clearly misclassifying this point over here. But now let's try and change your hyperplane. We'll keep every other parameter the same. The only thing that I'm going to change here is the fact that I'm going to get my hyperplane. Even the size of the margin, right? Even the size of the margin is going to be constant. This is still constant. I'm not touching this at all, right? So what I'm going to do now is bring a hyperplane which lies dead center between your negative hyperplane, which is this, and your positive hyperplane. And now, very obviously, we can see that your hyperplane correctly classifies this point as a circle. So what went wrong? What went wrong essentially was when this hyperplane got too close to this class, right? Then any data point which was very close to this hyperplane, let's put a hyperplane here and see what will happen. Any data point that is very close to this hyperplane will again be ambiguous, right? Because it's very close to your hyperplane. Like I said, data that's far away, the hyperplane does not need to worry about. It's only when it gets close to it that the hyperplane gets confused. That, okay, am I sure this belongs on this side? What if it actually belongs here, right? Because it's not very far from the decision boundary. If you're far from the decision boundary, then you know for a fact that you're well within your class, which you should be in. But this is what is the issue which occurs if you make even one of the margins very small, right? If you want to make one of them bigger. So that is pretty clear now that we need your hyperplane to lie dead center between your negative and positive hyperplanes. So great, lambda 1 and lambda 2 must have the same magnitude. You should have something like plus minus 50 or plus minus 10 or plus minus 2000 or anything. I'm sure some of you are wondering, why is it plus and minus 1, right? It can be plus minus 2000, it can be plus minus 0.005, it can be plus minus 3 as well if you want. Why 1? And the answer to that is pretty simple. It's just mathematical simplicity. Right? The entire vertex plus minus 1, because it's just simple and it's very convenient. And that's a pretty good answer, I'd say, because there is no other reason besides mathematical simplicity for taking plus and minus 1. So now that we have our equations of L1 and L2, right? If we have two equations, we can then compute the distance. And we'll first convert our vectors. So W vector is here again, some arbitrary vector m I cap plus n j cap. And your capital X vector, which is the position vector of your data point, can be given by xi plus yj. X and y are basically these are two classes, okay? So the value that your data point has in X and your value that your data point has in Y multiplied by the corresponding unit vectors. So this X over here isn't the same as this X. This X represents a vector and this X is obviously a class, okay? So just wanted to clear that out. Don't want people to be confused about that. And obviously, when we put this in vector format and convert it into Cartesian, we know what w dot x will be. This will just be mx plus ny, and your plus b is as it is. So your L1 and L2 equations, which were initially given by these two formulas, can now be rewritten in terms of Cartesian coordinates as this. And now that we have two equations of lines, right, then we can find the distance between them. And the distance d between L1 and L2, which is given by this formula, which I'm also sure most of you should be familiar with from 12th grade. This formula essentially just shows you the distance between any two lines, okay? And what this essentially is our margin, which is what we had defined it as originally, right? And your numerator actually in this case just becomes 2. Your denominator, which is square root of m square plus n square, is nothing but just the norm of w. And norm of w or L2 norm is basically just the same as writing the magnitude of vector w. The vector w is mi cap plus nj cap. The magnitude of this, we know this again, is square root of m square plus n square, which is what's represented by this notation over here. So after all of this calculation, we figured out finally that the margin's value, like the size of the margin, right, is just 2 upon the magnitude of vector w. That's it, nothing else. So we've already looked at this like initially, and we know for a fact that we should have a bigger margin for better classification. But the real question is, how far can we take this? How big can we make our margin, right? And it's pretty obvious that if I make my margin infinitely large, then I'm just going to misclassify every point, and I'm going to say that everything belongs to the same class, which is, or no class in general. Actually, they won't just belong to any particular class. I mean, it's just weird. So what constraint can I apply onto this such that I still, because if you remember, a hard margin tries to ensure that it's classifying all the training data correctly. That is its primary goal, right? And then once you are sure you're doing that, then you can increase the margin size as much as you can, as long as you're not misclassifying any training data. And that's the only constraint really that we have, because that's the objective of this algorithm, right? And that constraint, if I had to mathematically represent it, would be given by this, right? So I'm saying that for any particular class, sorry, any particular data point, if you have classified it correctly, then it should always satisfy this equation. So for any data point, let's say we'll take an example like this. We'll have a circle class and a triangle class. Okay. Now I'm saying that if you've classified it correctly, then this equation right here, which might not mean anything to you right now, should always be more than or equal to 1. Now I think it's pretty clear to everybody that if this is your hyperplane and this is L1 and L2, we know that L2 is represented by W dot X plus B is equal to 1. Okay. So any point ahead of L1, for them, W dot X plus B, right, will essentially be more than 1, right? And exactly at the hyperplane, W dot X plus B will be equal to 0. If you're exactly on L1, then W dot X plus B will be equal to -1. And if you're behind L1, then W dot X plus B will be less than 1, less than -1. So essentially for all positive samples, okay, I can say W dot X plus B is more than or equal to 1. It's equal to 1 if it lies exactly on the positive hyperplane, and if it lies beyond the hyperplane, then it's making an even larger distance from the decision boundary, so it will be greater than 1. And for negative samples, we can write this entire thing as being lesser than or equal to -1. Okay, so now that that is clear, for this thing, your y will be +1 and your W dot X plus B is obviously more than or equal to 1, right? So the product of these two will end up being greater than 1. 1 times more than 1 is also more than 1. Similarly, for this thing, your y is -1 and W dot X plus B is going to be less than or equal to -1. Now, -1 into something which is less than or equal to -1 is obviously more than or equal to 1, right? So again, the product of these two is also more than or equal to 1. Now let's introduce a misclassified point. So let's put a circle over here somewhere or a triangle here somewhere and see how these two act. Okay. So for this thing, your y is +1 because it's a triangle, y is +1. But now it's on the opposite side of the hyperplane. So your W dot X plus B actually becomes less than -1. And for this circle, your y is -1 because it's a circle, and W dot X plus B, because it lies ahead of the hyperplane, this will be more than or equal to +1. And if you notice, in this case, the product actually becomes less than or equal to -1. And over here as well, your product becomes less than or equal to -1. And this is purely because they are misclassified, right? They're misclassified. So that basically shows you that this criteria over here, which I originally introduced, this is nothing but a criteria, right? We can think of this as a criteria for correct classification. Okay, and that's it. So now that I've convinced you that this criteria is actually meaningful and means that you need to classify it correctly, then we can write whatever I've said so far in a more fancy way, a mathematical way, which is this equation down here. And all this means is find the arguments W and B which minimize this. And why minimize this? Because we're trying to maximize this. Maximizing 2 by W is the same as minimizing W by 2 or norm of W by 2. Okay. And essentially find W and B such that you're minimizing this given this constraint, and the constraint being don't misclassify any point. And that's exactly the definition of a hard margin. So far, does anybody have any doubts? Because we will now move on to a slightly newer topic. I think there are two people who have raised their hands. Yeah, can let you unmute. Yeah, Arun, Jay, do you have a doubt? Mm, Okay. Wait, you're still raising your hand. Let's see. Yeah. Do you have a doubt? Mm, okay, never mind. We will move to the next person. Vignesh, do you have any doubt? You've raised your hand. You can unmute if you like and ask it out. Mm, okay, I don't know why. All right, I guess you don't want to unmute your mic for some reason. Maybe you can put it in chat or get in touch with me later on. I'll have to move with the next topic now. So, okay. Yeah. So we've pretty well defined, like we've defined your hard margin very effectively now. The real issue is that we don't really come across data which can be separated by a hard margin in real life. And so what you'll usually come across is something which is either partially separable, as in where you'll have some amount of misclassification, or something which is completely not linearly separable. And for this, let's just look at two new concepts: a soft margin, which is what we're going to be talking about next, and kernels. Okay. So what is a soft margin and how does it differ from a hard margin? So the main criteria of a soft margin is that it basically allows some misclassification, in the sense that it basically will let you misclassify some training data points in order to make its margin bigger. And this kind of sounds very weird because we want a big margin, but we also don't want to misclassify training data. So why are we giving one more importance than the other in this case? So what's happening here is, let's look at a hard margin. Okay, this is very correctly classifying all the training data points, and it's got a pretty small margin though. And I've already said that this is not great because it creates ambiguity. You see these 2 points, they're very close to your hyperplane, and it's very ambiguous as to which class they should actually belong to. Because I mean, not for us as external viewers, but to the hyperplane. Whereas over here, right, it's got a much bigger margin, so it's pretty clear in the sense that it knows that things that are distinctly away from the hyperplane should belong to a specific class. But then it's misclassifying this right here, right? And that's a problem. So why, and is it really actually a problem, is what you need to ask yourself. And the real answer is no, it's not an issue. It's not that big of an issue because this we can think of as an anomaly. It's in the same class as these circles, right? The only difference is its features are anomalous and its position on the feature space is anomalous, right? So essentially, should we be allowing this to alter our decision to create a decision boundary, right? And the real answer is not really. If you go by every single anomaly in your training data set and try to fit your decision boundary to each and every anomalous point to ensure that you are not misclassifying any point in your training data point, that is basically the same as overfitting. And I'm pretty sure you'll have a decent understanding of overfitting if you've attended the previous 2 sessions. And it's kind of obvious here that this is overfitting. It's overfitting to reduce its training data, but that's bad because what's going to happen is it's going to perform worse than this on testing data. And essentially, the concept of a soft margin is to basically allow some misclassification on your training data so that we don't overfit, right? Such that we don't essentially end up performing badly on our test data. That's why we've brought about the concept of allowing some misclassification, relaxing these constraints of the hard margin. And to put that to the test, I added a test data point of my own, which is this bigger plus sign that you'll see over here. And like I expected, it's pretty obvious that this one is correctly classifying the test data, and this one is misclassifying it, right? And this is essentially what I wanted to show you, is that it's still good to have, you should not create an extremely small margin just because you want to lower your training error. This is what happens when you overfit, right? So now, how do we create the soft margin, right? That's the main question that we should have now. And the way we do this is we add two more terms to our original equation, which is this zeta and a c. So first let's look at zeta, which is this right here. So this is how we define zeta. For all correctly classified points, your zeta is 0, okay? And the way we define zeta for incorrectly classified points is basically its distance from its correct hyperplane. So if you look at this graph here, that illustrates it pretty well. there is a circle here, and it should actually be in this class, and this is its correct hyperplane, right? So this distance over here will be zeta for this particular data point. Similarly, this is a square, and this is its correct hyperplane, and this distance over here is essentially what will be your zeta for this square, this data point over here. Okay, and now that that is done, we can now basically what we do is we create a summation of all the zetas, right, which shows you how much you've classified and how badly you classified. Okay, so essentially, if you classified nothing incorrectly, your entire training classification is correct, then naturally zeta for all of this, right, all your zetas will basically be zero because you classified everything correctly. And let's say you have a massive value for the summation. That means you've classified multiple points wrong. And I mean, it can mean that you've classified multiple points wrong by a certain amount. It could also mean everything is correctly classified and one point is hugely misclassified. And I mean, basically, this shows you the extent of misclassification. This summation right here. See, we'll come to later on in like just a few minutes. So again, we have created this sum and we added it to our norm of w by 2. And now we're saying minimize this entire sum. And as you notice, there is no constraint over here, right? Like we had in a hard march. And that's the whole point, is that there is no constraint because we have allowed some misclassification. Now you'll probably be wondering how much misclassification are you allowing exactly? We'll come to that in a bit. So this statement here just means find your argument, as in just find w and b, right? Your arguments w and b, which minimize this entire function over here. Okay, and the cost function representation of this line of math that we've written over here is basically this. This is how we define our cost function, and I'll now explain both the terms in the cost function, right? The first one should be fairly easy to understand. You've taken norm of w by 2 as the first term. Okay, so norm of w square, sorry, yeah, norm of w the whole square by 2 plus c times your summation of max of 0. And for now, I'm just going to be calling this term right here 1 minus y times w dot x plus b. We'll just call this epsilon for brevity. Okay, so this is epsilon. Epsilon is just basically this over here. And what your max function does is it outputs whichever one of the two is greater. So if 0 is greater, it will give you 0 as a result. And if epsilon is greater, it will give you epsilon. So for all correctly classified points, right, we know that yi times w dot x plus b should be more than or equal to 1, which would basically mean your epsilon becomes less than 0, right? Because, and this basically means that the max function is going to output 0 because 0 is bigger than epsilon. And for all incorrectly classified points, your yi times w dot x plus b will be less than or equal to -1, which means your epsilon will now be more than 0, and the output of your max function is going to be epsilon. So essentially, if you're correctly classifying something, it's going to output 0, and if you're incorrectly classifying something, it's going to output epsilon. And the more you incorrectly classify, the bigger this sum is going to get. And the bigger this sum gets, that shows you that you've misclassified that much more, right? And how do you reduce this sum, or how do you reduce the cost function rather, is by reducing either of these two values. So if you make this thing smaller, right, then that's going to make your margin bigger. And if we make this term smaller, right, that means the extent of misclassification becomes smaller. So we'll have better classification on, and this is very important, training data set. This does not say anything about the test. It just means you have better classification on your training data set if you make this smaller. Okay, and that is how both of these functions act in your cost function. Now coming to C, right? What is your C doing? So now you can understand, you notice one thing, that if your C is very big, right, what's going to happen if your C is very big, right, this second term overall becomes much bigger. And if your second term becomes bigger, if C is bigger, that essentially means that your cost function is now more dependent on reducing this, and reducing this is equivalent to reducing misclassification. So if your C is bigger, your cost function is now focusing more on reducing misclassification, because that makes up a bigger part of your cost function, right? If your C is a massive value, let's say it's like 500 or something, and that means this is very small compared to this. So we can say this is almost insignificant, and your cost function almost entirely depends on reducing misclassification. The converse can be thought of as in this way: if C is very small, then this second term becomes almost negligible. And if your C is very small, your second term becomes very negligible, then your cost function is almost entirely dependent on this, and dependent on reducing this, which is, in other words, dependent on increasing the size of the margin. Now, on the basis of what I've spoken about C and overfitting, underfitting, and the margin size, I have one more poll over here, which we'll activate now. So let's just go back to the and the answer for this we will discuss in detail. I just want to see okay. I want to see how much people have understood so far. So sorry. Okay. So I'll give you guys some time to answer this. And this is multiple. This has, I mean, I actually I can tell this to you. This has actually two options correct. So okay, so 50 people have answered. Okay, not what I expected to see, but fine. Yeah, these are the correct answers, and I think you all got the first one correct. A small value of C. So what happens if C is small, right? If C is small, right, what's going to happen is your cost function is going to be more dependent on increasing the size of the margin, right? And essentially what that's going to do is it'll depend lesser, it'll basically underfit your data and give you a higher training error. Underfitting your training data and giving your higher training error is basically the same thing, right? So a small value of C does two things. If it underfits the training data, right, then it obviously will also give you a higher training error and vice versa. You all got one of the options right. So the other one is the equivalent statement of the first option actually. So that's all right. We can now look at this in a little more detail. So yeah, so a large value of C, right? Like I said, if your C is very large, your cost function will depend it'll depend heavily on, if your C is very large, it will depend on the classification term more than the margin term. And that means it's going to try to classify better. And it's going to focus mainly on classification at the cost of creating a big margin. So it will create a smaller margin if it has to, but it will classify better. And that is exactly what our hard margin does. So it's acting like a hard margin. It's not exactly a hard margin because it still does allow some misclassification, but it will allow lesser misclassification compared to a smaller value of C. And obviously, if you act like a hard margin and you're allowing lesser misclassification, your training error is going to be low, right? But the risk with this is that if you make it too low, you're essentially overfitting, which is what the third point is. And the small value of C is exactly the opposite. You will misclassify more, right? And if you do misclassify more, that is essentially that. And what that means is if you misclassify extremely, like a lot, you misclassify way too much, that means your model isn't even learning. And if it's not learning, you're basically underfit the training data. And something which allows more misclassification in general is something which would act like a soft margin, right? Or at least the opposite of a hard margin. And that is all we have for margins, soft margins at least. We will now go to kernels in SVMs. And this is the second concept that we will introduce in order to be able to classify something which is a non-linear SVM problem. So this is the first concept we're introducing, which actually deals with non-linear SVMs, right? And its sole purpose is to deal with such type of data sets. Now, look at this. This is like the example I showed you with the circle. where there is no one line that you can draw to actually correctly classify the red and the blue classes. There isn't actually one line, and you can try, you won't find a line. The thing that works over here is a boundary, like you can see over here. But how do we write w dot x plus b for that? Right? It's not linear. So what are we going to do? So what we do actually in cases like this, and I'm sure you can see from the diagram, is we add a new feature. You add a new feature of your own. So you can have, it can be anything. You can have features like x1, x2, and x2 square. x2 square can act as your third feature. So your x3 can be x2 square, or it can be anything. It can be x1 into x2, whatever you want. You essentially add a third feature, right? Create a third feature of your own, and then you now have three different parameters to separate your data on the basis of, if that makes sense, right? Instead of just two. And the more parameters you have to separate your data on, the more separable your data becomes, right? Because your data is now more distinguished. You have not just two, but three ways to now tell me how data sets or data points in different classes are distinct from each other. And that's the whole reason we're adding a new feature. We're adding dimensionality to create more features and increase the separability of our data. And then you can see this is actually a plane. So this feature space is actually linearly separable, right? We went from a non-linearly separable input space to a linearly separable feature space by adding a new feature. So we do this, then create our new hyperplane, right? So we'll first add our new feature, then calculate all the new coordinates in your feature space, right? We compute the new coordinates, plot it in your feature space, create your new hyperplane, find the equivalent of this hyperplane. So represent this two-dimensional hyperplane, which is in a three-dimensional feature space. So we represent this as a one-dimensional line in your two-dimensional input space. Now, the main issue with this is that computation is a massive problem with this, because you have to now sit in. This is pretty small. We have like what, 7 data points in total. Sorry, 10 data points in total. Now, with 10 data points is all, it's all fine. But like when your data size increases, right? That's going to be it's your computer is the one who's computing this, right? You're not doing this manually, and that computer is going to have that computer is going to have a problem sitting and calculating all the new coordinates for every single data point um, in your training data, and mapping it to your feature space, and then finding your hyperplane, and then bringing the representation back into your input space. That is computationally very heavy, and with heavy computation we have computational costs, and this is essentially the main issue, is that it's expensive unnecessarily. Why is it unnecessary? Because we have kernels. Kernels makes this entire getting into a feature space unnecessary. So what are kernels exactly doing, and why are they so magical, right? And why do they save us all this
Rishi,
excess computation? Yes.
yeah, before getting into kernels, if possible, can you once share the QR code for the attendance?
Oh sure, yeah, yeah, I'll do that.
Yeah, all right. You can give
Yeah,
them
this
some
is the.
time, like probably keep the QR code for 2 minutes or one or 2 minutes, and then you can continue.
All right, no problem. Yeah.
Yeah, guys. So everyone, please scan the QR code. So this is not applicable only for the YouTube live stream people. This is applicable for everyone. From now on, everyone, whether you are attending the session on Microsoft Teams or whether you are attending on live stream, you should be scanning the QR code. We'll be showing the QR code again later on in the session. So even if you miss now, don't worry, don't panic. We'll be sharing the QR code again, so you can scan it later. But let me repeat again, we won't be sharing the links either on the YouTube chat or in the WhatsApp groups. And few of you were asking how do we scan the QR code? You can make use of Google Lens. And if you are on your mobile, take a screenshot of it and then open your Google Lens, and from the gallery, take the screenshot and scan it. Yeah, I guess Rishi, you can resume.
Yeah, okay. So yeah. Um okay. So what people noticed was once you did a lot of math, and what's that math? Essentially, whatever computation I showed you on the previous page, you do this, you find your loss function, you perform like gradient descent on your loss function, come to a minimum, and that will give you your W. And I'm pretty sure you're familiar with all these terms from the previous sessions if you watched them. Um, and essentially, what you come down to, your final equation of the plane, is basically something like this, is what people found out. And this right here, I know it looks very weird, but it's basically just a function of the dot products of your input vectors in the input space itself. And I said input space, not feature space. Input space is this right here. So if your final hyperplane is essentially just a function, so this k of xi and x of a, which is basically your k is what we call your kernel function essentially, and that's given by something like this. This essentially represents any function which is a function of the dot products of two vectors xi and xj. Now in this case, your xi and x are basically two vectors in your input space itself. So what people realize is was that they never really had to calculate the corresponding coordinates in your feature space. You never really had to do all that mapping because your final result comes down to this. It only depends on the relation of two like data points in the input space itself. And you can save all that computation by just directly using your kernel function. So your kernel essentially is the end step, or if you can think of it that way, you can think of it that way. Is it's an end step to all your math at the end of it, right? This is what it comes down to. No matter what it is, it always comes down to something like this. So this is why kernels save you a lot of money and a lot of time, and this is why these functions are actually so insane. So let's look at two kernels. We'll be looking at two kernels in detail right now. One is the polynomial kernel, and yeah. So it's given by this function. So your k of x and x dash is essentially given by this function over here. Now, one thing I'll tell people who are probably confused at this point is don't worry about the math too much or why things are the way that, why kernels are working the way they are, because the math is pretty intensive for this. What you should understand is what the kernel is doing and how your boundary looks, and more importantly, the hyperparameter tuning. That is something you'll use much more in practice than actually understanding the math, because that's just a bunch of equations and a lot of algebra. So right here we have, so this right here, this is actually just a notation for dot product of x and x dash, right? So that's nothing else. So this is essentially a function of the dot products. So your polynomial kernel is calculating the dot products of your input vectors in the original space itself, right? Does not need to calculate in the feature space. It does that, finds the similarities between two data points, right? Finds the similarities, and on the basis of these similarities, it will then create a polynomial boundary. And you can see what the boundary looks like as well. And this is non-linear, and it obviously has a polynomial-like shape. Hence the name polynomial kernel, right? Now the main important part, hyperparameter tuning. Now we've already looked at this in detail, right? C value we've already covered, and we know that a high C, like a large C value, will focus more on classification, gives a lower training error. But if it's too large, you might overfit. And similarly, a small C value, we know this. What I really wanted to focus on is D. D is the degree of the polynomial, and the degree of the polynomial basically determines if your polynomial is going to look like this. If your polynomial is going to be 1 degree, like a 1 degree boundary, or if it's going to be something like a 2 degree boundary, or a 3 degree boundary, or a 4 degree, and so on, right? Now, the real issue when are we going to overfit? Okay, so if I had some data which was like this, okay, just ignore the bad drawing. I'm really sorry. Um, and now if I start creating a hyperplane like this, right? If I start doing something like this, you see what I'm doing over here? I'm overfitting. I'm trying to make sure that I have no training error whatsoever, and that's basically overfitting. This is a polynomial with a very high degree, right? Hence the number of curves in it. So very high degree, if you want to visualize it spatially, is essentially converting. So like how we converted in the first example from 2 degrees to 3 degrees, right? if I were to convert from 2 to 5 degrees, then your polynomial, the degree of the polynomial that separates would be 5, right? And if we're creating more parameters to separate on, we're essentially creating a more complex model. And that happens when we have more features to separate on, right? Is when we add more features, we have a more complicated model, which happens by increasing the degree of the polynomial. And similarly, if we have a lower degree, then the separation boundary will be a polynomial for lower degree, right? And that will mean that you have lesser number of features to distinguish your two classes on, right? And essentially that's a simpler model. Now this does not mean that we actually compute those new features. It's the equivalent of doing that, okay? So I've already showed you why a higher degree might overfit, because you have multiple curves. So you actually end up really overfitting the training data. And similarly, a lower degree will end up underfitting your training data. This is like, so we have to actually find a balance between the two, and that's the essence of hyperparameter tuning. The next is RBF kernel. Okay, this is another kernel function. This basically looks at the similarities and based off of how close 2 points are to each other. Okay, so the mathematical function is this. Don't really worry too much about this, right? Of course, we know that this is the distance. So between x1 and x2, there are two vectors. The data points, we find the distance between them. The square of that is what's represented over here. Now, essentially, we already know what C does, so that's fine, right? Gamma is what we're going to be looking at. That's the only other hyperparameter of the game. So let's read this one. Gamma defines how much influence a single training example has. Okay, the larger the gamma is, the closer other examples must be to it to be affected. Okay, why? Because let's look at this. If your gamma value is very large, this overall term becomes very, very negative. So in order to make it not very largely negative, we have to reduce the magnitude of this number here. And since your gamma is very large, the way we do that is by reducing this. Okay. And what's going to happen if I have e raised to minus 38 or something? Your kernel function is going to ignore it because it's e raised to minus 38. It's something which is so small it's practically zero. It has no effect on the kernel function, right? So we make this small so that we get some more finite value, like e raised to minus 1 or minus 2, which is still not practically zero. Okay. And what are we doing when making this smaller? This basically means that two things need to be very close so that this distance becomes smaller to counteract this gamma becoming very large, right? And that is what they mean by two things have to be very close to each other to be affected. So for the gamma, like to be affected by each other. And naturally, if your gamma is very large, right, then you're going to look very close, like around you, like this. You only look at the data points around you to decide which class you are in, which are very close to you and just around you. You won't look too far away, and that is basically overfitting, right? And if your gamma is very small, then even data points which are very far away from where you're at will also affect your decision, which will also not happen because then you're not learning anything. If you look at the entire data, like the entire space to decide which boundary you're looking at, you're not really observing any patterns. So you're supposed to decide how close you're looking around you to find your boundary. And you actually get a better intuition of what this means when you learn KNNs in the second half. So for now, that's all I have for RBF kernels. These are just some advantages and disadvantages of SKMs. We know that, like I said, if it's very well separated, SKMs are going to work better. Okay. And now we know because of kernels that in higher dimensional spaces also we can create a high dimensional boundary. That's not an issue. So they will work more efficiently here because higher the dimensions, more features you have to distinguish. So again, they're more separable. They're relatively memory efficient. Okay. Now, kernels are a massive strength of this, and you'll see this in a while that if you choose the right kernel and the right hyperparameters, you can pretty much solve any complex problem for a small enough data set. And this scales relatively well to high dimensional data as well, because like we showed you, kernels will basically do the same job as increasing the features and increasing the data, the dimensions. Now, this is not suitable for very large data sets because computation becomes very long and very expensive at this point. And this will not perform well when there is overlap. So overlap is basically something like this, where you see there is some amount of overlap, like triangles and circles are here and they're kind of mixed. The boundary is not clear. That's essentially overlap, is when the boundary is it looks kind of diffused. And in such cases, obviously finding a boundary is also harder because overlap is this opposite of well separated. And now one thing which is very important over here is that the support vector machines or hyperplane does not really consider these 2 points as different. This and this are equally belonging to class A. and it does not distinguish between these 2 points. Although this point has a lower probability of belonging to class A because it's very close to the hyperplane. So we can't be as sure. Whereas this one is very far away from the hyperplane, so we can be sure that it belongs to class A. So essentially, when we have no probabilistic approach and it's all binary, right, in the way we're looking at things, that can be an issue because probability is also important. I can't say your 30% chance of having obesity and 70% chance of not being obese. It's just you're either obese or not obese. You're either tall or short. It's just binary, and that's not always great. And the last two things are what I've been saying. Choosing your kernel is not always easy, and tuning your hyperparameters is also not easy because looking at 2 and 3 dimensional data is easy, but when you come to higher dimensions, you can't even visualize their impact. Like 5 dimensions, we can't plot anywhere. And that's about it for now. I guess I can probably, we've already looked at the code implementation. So we already looked at the attendance. I think I've given you all a few minutes to scan this. Maybe I can wait for another 30 seconds if you want. And then we'll move to the coding implementation for this. Yeah, let's go to the code. Now, we're not going to get into too much detail about the syntactical features of the code, but more importantly, what the code is doing. So I've made my imports over here, okay? And I am using the iris dataset. Essentially, there are 3 flowers in this, Setosa and versicolor and virginica. We said we're going to be looking at classification of just 2 classes, okay? And classification of 2 classes. And we only want 2 features because we want to plot a feature space, right? Which is 2-dimensional on your laptop screen, which is easy to visualize. So we'll be dropping these 2 features and only be classifying on the basis of these 2 features. And your 2 classes will be Setosa and versicolor. So over here, I'm basically dropping the last 50 rows, actually only contain virginica flowers. So I'm just reading the first 100 rows out of the 150. So this effectively drops your virginica, which is what we wanted to do. Oh, I'm so sorry. And this is dropping your 2 features over here, which is what I said. So now we have 2 classes and 2 features. You print the data, check, and it's correct. You have 2 classes and only 2 features. Now we're extracting your data. Okay, so this is very simple. We have a column here, your species column. We're applying using the apply over here, the lambda function on the species column, which basically it does this. If a value in the species column is Setosa, it will give you 1. If it's not Setosa, it will give you -1. So the other one is versicolor. So if it's versicolor, it gives you -1. We then take your sepal and petal length columns from your data frame, convert it to a NumPy array, and store them in these arrays respectively. And then you basically, this np.transpose is essentially just taking your 2 arrays and pairing them up, which will be your data set later on. And your data set is essentially a 100 by 2 dimension. It has 100 flowers and 2 features, right? 2 features, which is your sepal and petal length for each of those 100 flowers. And this is plotting your data. So we're going to using matplotlib, and your data looks something like this. So your x-axis will have your sepal length and your y-axis will contain your petal length. And this is what Setosa looks like, and this is what versicolor looks like. And it's pretty clear that this is linearly separable. We have no doubt in that. This is shuffling your data set. Essentially, you're taking your x and target and you're shuffling them so that there is no inherent bias to remove that from the data set. And you assign them to x and y, which will now be your train and like your training data set is what you're gonna create that from this. So your train test split takes your 2 arrays, splits them in a 9:1 ratio, and creates your train data and your test data, which is this, right? And like it should be, your train shape is 90 by 2 because your x was 100 by 2, and this should be 90% of that. So your test automatically becomes 10 by 2. Now coming to actually implementing your SVC, your support vector classification, right? So we import this from sklearn. This is basically a way to measure accuracy, which is from sklearn metrics. And your classifier over here, so this entire function essentially returns a classifier, which we assign to the variable CLF. Your classifier is a linear kernel because it's obviously linearly separable. We can see that. And when I mentioned when I mentioned that support vector machines do not have a probabilistic representation to them, so sklearn actually gives you an option to calculate the probability of a particular class, or data point belonging to a particular class. So this is because this is a feature of sklearn. This does not mean the actual model, the algorithm itself, SVM, does not have a probabilistic nature to it. It has a binary nature to it. However, sklearn allows us to find the probabilities, so that's good. That increases our accuracy essentially. Um, and then this is pretty standard. You train your classifier on your X-train and your true label, which is this. You then use your classifier to predict on the test data set, and you assign those values to your Y prediction. And then I'm just printing the accuracy score, and I'm comparing your predicted values and your test values, and the accuracy is 1. And it should be 1 because it's pretty clear that it should be 1 because it's a very well separated data set. So any linear SVM will also work pretty well on this. The next part of this is essentially just plotting your data. So initially I'm plotting my two classes, right? And this is to plot your line of best fit using what we've gotten through this. So when you plot the line of best fit, it looks something like this right here. And it's pretty clear that this is very well separated, and it should also have 100% accuracy because it will perform pretty perfectly on the test data. Now I am going to get a new data frame, which is not linearly separable. And you'll see this in a second. So I've got your sleep, health, and lifestyle data set from Kaggle. And since I only want 2 features to separate on, I am going to drop all but 2 features, right? I'm going to drop all but 2 features. And what you will find is over here, you have sleep duration, quality of sleep, and sleep disorder is what we're classifying on. This drop NA essentially means you're dropping all blank terms. So when you print your data frame, you should see sleep duration and quality of sleep. These will be the 2 features that we're going to use to classify. And what we will classify is people. We'll classify them into 2 classes. If you have some sleeping disorder, or if you have no sleeping disorder at all. That is how we're classifying. So this part of the data is pretty much identical to the previous one, right? We're doing exactly the same thing. We're creating a target array which will contain +1s and -1s depending on whether or not you have a sleep order. This is your sleep disorder, sorry. This is your ground truth array. You create your quality, create 2 more arrays for your 2 features, 1 array for the ground truth, and you create your verification data, which we'll be using later on. And of course, you transpose these so that you create your input data set, right? Your training data, which you use this to create a train and test data essentially. So you pair them up essentially, and you get this has 374 rows. So, and you have 2 features in this. So as expected, it should be 374 by 2, the shape of your X data. And then of course we plot our data. We want to see what it looks like. And this is what I meant. This is non-linearly separable. You can't draw one line to distinguish both of these effectively. And this is where we'll use kernels. So I'm going to do the same steps again. I'm going to use sklearn. We will shuffle our your training, basically your input data and your ground truth to remove any inherent bias. One thing I didn't mention earlier is this random state equal to 42. This is basically, it's creating some random shuffling of both of these such that you can reproduce it each time. If you keep 42, each time you shuffle, you'll reproduce the same form of shuffling and get the same shuffling each time. So that I can, and that's the purpose of this 42. And random state is essentially just shuffling. We're giving it one value, so it reproduces the same thing over and over again. And then of course you train and test, you're doing your train and test split. Here I'm taking 80% because I saw that it's going to be better for me to explain what's going on with an 80% split. The results are almost identical with 90, but we'll do 80 here. And your train shape is this. You have 374 by 2, and 80% of that would be 299 by 2. So ignore everything else for a time being. We're now implementing SVM using polynomial kernels, and look what's going on over here. Okay. I'm again making a classifier. It's a polynomial kernel. We're giving it a degree I, which I'll tell you what it is later. Coefficient.0 is just your R hyperparameter in your polynomial kernel. If you look at the slides, you have gamma, R, and D, right? This is your D, this is your R, okay? Probability is true. We've already gone over this once. So you train your classifier on your X train and Y train, right? You predict based off of what your classifier has learned on the X test, assign those values to your Y prediction. And now I've created a degree array where your I essentially iterates through this. So I want to see what the effect of degree is on accuracy. So for each accuracy, I will predict this and I will append my accuracy score to my accuracy array, which is over here. Okay. And then I'm going to print these and I'm going to plot these two arrays essentially. And it looks something like this. This is your accuracy of 1 degree, 2 degree, 3 degree, 4 and 5. And like I said, lower degrees will underfit, higher degrees will overfit, and hence they'll both be less accurate. So in this case, it seems to be that the third degree is what is giving you the highest accuracy. And this shows you what underfitting and overfitting looks like actually in accuracy terms. Okay. I'm doing the exact same thing with RBF kernels, right? Instead of now changing degree, because degree is irrelevant for RBF kernels, your hyperparameter here is gamma. I'm going to be changing gamma and then finding. So the same code pretty much, right, in both cases. One more thing I need to mention is the CLF.none that I'm doing is for every iteration, you want to clear anything that your classifier has learned in the previous iteration. So we clear it and then move to the next iteration so that there is no previous gradient stored in the classifier. And again, you have a bunch of gamma values, you train your model, predict it, and append your accuracy values. And when you plot it, this is exactly what we should see. Is for a very low gamma value, you'll end up obviously with a lower accuracy and with a very high gamma value. So in this case, a higher gamma value is going to overfit, right? We know that. And a very low gamma value is going to underfit your data. And that's exactly what's being illustrated over here. And that is all I have. I just wanted to show you this as a graphical illustration of how hyperparameters actually work. This is for the code implementation. My presentation. I guess now I can take a few doubts if you all have any. So I'll just open the Slido to see if there's any doubts over there. Okay, so there's one doubt. Suppose we have D1 equal to D2, but D1 plus D2 does not give the maximum margin, and we have unequal D1 and D2, but close. Do they give a maximum margin? Which one is better? See, maximum margin is something which we have to like train and find on our own. D1 is equal to D2 always, period. And D1 plus D2 will not always give you the maximum margin, right? That's the entire point of the soft margin thing, is when we will decide how big of a margin to give you. The goal is not to always find the maximum margin. It's to find the right balance between the maximum, like between the size of the margin and misclassification. So your D1 plus D2 is the size of your margin. How big that is based on your hyperparameters. So we're not looking to find the maximum margin, if that makes it clearer. Okay, there's no more doubts related to SVMs at least. That's what I can see. Rutvik, can I unmute people and answer doubts?
Yeah, that works. And also, if possible, can you share the QR code again for the attendance? Few of
Yeah,
them have
yeah.
faced an issue earlier. We'll
Yeah,
just resolve
right.
those. Yeah.
This is right here, yeah.
Rutik, I think I will do that.
Okay,
The
yeah,
beginning of
actually,
my presentation.
I think
Okay,
yeah, I
fine.
can.
That's fine. But still, Rishi, can you share once, because people are
Oh, yeah.
facing some issue with the QR code?
Sure, no problem.
Yeah.
I guess in the meanwhile, you can probably unmute somebody if they have a doubt. And
Yeah. Can you share your screen, Rishi?
yeah, sure. Oh, I'm so sorry. I forgot I was not sharing. Sorry. Yeah. Sorry. Is it visible now?
Yeah, it's visible.
Okay.
Guys, can you react with a thumbs up if the QR code is working fine? Few of the people have messaged on the group saying that it has reached the maximum limit and hence they're not able to scan the QR code. you can see a React option at the top. Click on that. That will be helpful. All right. I guess a few of them have replied on the WhatsApp group saying that it still shows maximum limit has been reached. Fine. We'll resolve that issue. When Anupam is sharing the QR code, he'll share the updated one so that the people who weren't able to scan earlier, they can scan it next. And Rishi, I guess you can try to unmute the people who have raised their hands and clarify a few of the doubts. Okay. And we can take a 5 minutes break and probably we can again begin at 6:30. Meanwhile, you can just clear some of the doubts.
Yeah, sounds good. Yeah, okay. I think Bhavdeep, I've let you unmute if you like. Okay, he has it. Okay, I guess I can unmute Vignesh. You can ask your doubt using your mic if you like. Vignesh, I've given you mic access. You can unmute. Should we just give everybody mic access and whoever has a doubt can unmute and ask real quick?
All right, you can do that.
Okay, okay. Yeah, I've allowed mic access for everybody, so anybody who has a doubt can unmute and ask your doubt.
Hey, hello, can you resolve this attendance issue, please? Still, we are not able to get done.
Sorry.
That attendance issue. Still,
Yeah,
like,
you'll so in the second half of the session you'll find the QR link again. They'll resolve whatever issues there. It's saying maximum limit reached, so you can find it in the second half at 6:30. Okay, like we'll start the session at 6:30.
okay, I tried scanning in first half also, and second time also same. So, like, okay.
Yeah, they're working on the issue. We'll work on the issue and resolve it. You can try again in the second session. We'll give you multiple times like chances to scan it.
Can you please turn on the attendance also on in the Teams, the automatic attendance thing, so that like even like in case.
We'll look into that. Is there any doubt regarding like the topic itself?
Do we need to get into the details of the working of the kernels?
No. So that's the thing. You should try and understand how the hyperparameters are working for the kernels and just understand what the kernel is doing. And the main thing is that it's basically allowing you to like avoid all those excess computations by preventing the need to map to a feature space and essentially just try and understand that and how the hyperparameters are working. The math behind it is something which is very extensive. I guess if you really want resources to understand it, I can give them to you after the session, but really not that important. Yeah. Anybody else? Okay, then I think we can proceed and take to the 5-minute break for the session, I guess. Is that okay?
Yeah,
Ritik?
that works. Yeah, that works.
Okay.
You can disable the mic access for everyone. We'll take a 5 minutes break and we'll again begin at 6:30.
All right. Yeah. Thank you.
Yeah, I guess now we can begin the second half of the session. Anupam, you can start sharing your screen.
Yes. Can you see the screen?
Not yet. No.
Wait. Can you say it now?
Could you check again? Hold on for a minute, guys. We are facing some technical issues.
Yes, I guess now you can see the screen, right?
Yep, now it's working. Cool.
Yeah, yes. So, Rishi had a very wonderful presentation regarding SVMs, and now I will be taking the second half of the session regarding KNN algorithm and naive Bayes, which are also classifiers. So, I heard that you had some problem regarding the attendance link. So this is an updated attendance QR code. So those guys who had some problem regarding the old attendance QR code can scan this QR code.
Give them a minute or so that they can scan the QR code.
Sure.
Yeah. I hope the QR code is working. If you guys can react with a thumbs up, that should work. Or you can even message on the WhatsApp groups.
I think we'll move on.
Yeah, I guess we can move on. Yeah,
yes.
You can continue on.
So after Rishi's wonderful presentation regarding SVMs, you'll be still in the hang of SVMs, right? So it won't be very appropriate for me to introduce a completely new classifier, right? So let's have a smooth transition from SVMs to the new algorithm that I'm going to introduce to you. So let us begin with the simplest case of a classification problem, the famous triangle and the circle problem. So we only have two samples in the initial data set, one triangle and one circle. And how do we go about classifying these two? And we have two features as well, right? So it's easier for you to easier for us to visualize. Now, Rishi would suggest, well, we will just draw a straight line in between triangle and the circle, right? That's what we call the hyperplane. And since this new point that I'm introducing, okay, is going to be a triangle since it lies left to the decision boundary or the hyperplane, right? So this is perfectly clear to you. Now, think about it in this way. The new point introduced, which incidentally falls into the left half plane, is going to be closer to the triangle than the circle, right? And just try to think about all the points that lie left to the hyperplane, left to this decision boundary. All those points are going to lie closer to this triangle than to this circle, right? Okay, so have this picture in your mind, and now from that picture erase that decision boundary, and just try to think in this terms. This new point, or this new data point, which lies closer to the triangle than to the circle, is going to be a triangle since it lies closer to the triangle than the circle, right? It's in this case, it's an equivalent way of thinking, right? All the points that lies left of this hyperplane lies closer to the triangle than to the circle, and they're going to be classified as triangles because they lie left to the hyperplane, right? And in the alternative way of thinking, we can also say that it's going to be a triangle because it lies closer to the triangle than the circle, right? So find out the near. So what's my algorithm? What's the new algorithm that I'm going to introduce to you? Find out the nearest known object closer to it, and then classify it under the same label. But of course, this is a very simple example, a rudimentary example. Let's go into a somewhat more complex example. And in this case, we can say 8 samples in the initial data set, 4 triangles and 4 circles. And here also, we are employing an SVM classifier to classify, and we will have a line that cuts halfway between the set of triangles and the set of circles, right? And clearly this square here, or this unknown object here, is definitely going to be a triangle since it lies to the left of the decision boundary. It lies along with the triangles, right? But now I have introduced an alternative way of thinking, right? I have introduced to you an alternative way of thinking. What's that? Erase the decision boundary and find out its neighbors. Find out the neighbors of the square. Find out the neighbors of this unknown object, right? And then classify it under the same label. So we know from SVM classifier that this is going to be a triangle, right? And what does the new way of thinking leads us to think? This square right here is likely to be a triangle because it has more number of neighbors as triangles rather than circles. Let's say I'm considering its 4 nearest neighbors, the 4 nearest neighbors, and I can see this 1 circle and 3 triangles. So since the number of triangles are more than, that is 3, is more than the number of circles that lie close to it, we can safely say that this square here is likely to be a triangle, and we can classify it under the label of a triangle, right? But in this case, there's a hidden ambiguity, right? You might have spotted that. I have just randomly said 4. It could be 1, it could be 2, it could be 3, it could be 4. How many neighbors are we to consider? How many neighbors are we to take votes from? Right? Here we took votes from 4 of them, right? So, and this also may lead you to think that both the classification schemes are identical. SVM introduced by Rishi is exactly the same classification scheme as this new algorithm, but it's not. Say I have this guy here, okay, this blue man here who lives in Besançon, and we want to know if he's a French or German, okay? So he lies in the territorial region of France, and this is the territorial region of Germany. So we want to know if this guy is French or German. So this guy here, okay? So let's just assume that it's Rishi. He says that the man has to be French since he is within the territorial region of France, right? This guy here has studied all the people. He has studied all the people of France and Germany and has drawn definite territories, and then argues that this man here has to be French because he belongs to the territorial region of France. And okay, assume this is me, okay? And this guy is saying the man has to be French since most of the guys he's interacting with is French. Like this guy's wife is a French, his mother is a French, his father is a French, the shopkeeper is buying goods from his French, and hence most of the guys he's interacting is from French, and that is a reflection of his own identity, and hence this guy is also French, right? And we know that both of the guys, the first guy and the second guy, derived a conclusion or reached a conclusion in distinct ways. The same conclusion, mind you, the same conclusion in distinct ways. Both could be wrong, right? Both could be wrong. Both could be correct. Both could be wrong in the sense that guy could be a German tourist. Or both could be correct. He could be a French native. Or only one of them might be accurate. Like this may be a, say, Besancon, the population that is native to Besancon is German, right? So it's a German minority lives in Besancon. So in that case, the first guy would say that he is a French regardless because he lives within the territorial region of France. But the second guy would say that he is a German because now he lives in a minor territorial region of Germany, right? In which consists of German, which consists of ethnic Germans. So this guy is interacting with Germans, and that persuades this man to classify him as a German because most of the guys is interacting with this German, even though he lies within the territorial region of France, right? And so this is one way in which only one of them might be accurate. So I'm saying this because I don't want you to think that both the classification schemes produce identical results, right? Both have their own outliers, both have their own inaccuracies, and even though sometimes the conclusion may be overlapping, the ways of thinking are distinct and can produce different results, right? And this, now you know the basics of KNN algorithm. Now I will introduce this thing formally, okay? KNN essentially means K nearest neighbors, okay? K nearest neighbors. KNN looks for its K nearest neighbors by their distances, right? By their distances, and then mark the class of the point according to the majority of the neighbors. This is what I did in the triangle and the circle example, right? I took the 4 nearest neighbors and then took a majority vote decision and then classified it under the same label, right? The algorithm is extremely simple. I spent some time introducing it to you, but it's actually an extremely simple algorithm, right? Right, now some jargon. So so 3 technical terms that you may come across. So I know that my audience is a very intellectually hungry people, and you might read more about KNN in articles after this session. And at that time, you may come across these terms, lazy learning, non-parametric, right? And you don't have to be intimidated by these terms. So I will explain what all refer to. So in case of lazy learning, you have learned about linear regression, logistic regression, and now SVMs, right? In all these learning models, we have a training data set, and on the basis of the training data set, we will have something to optimize, right? Some function to optimize, right? And that optimization was dependent upon the features of the samples that we have collected in the training data set, right? And say in the case of SVMs, right? Where did this line come from? Did it come from what Rishi initially did? He initially had a random line, right? He had a random line, and then he used this optimization while training. This line got better and better at classifying, and eventually at the end of the training phase, it became the best line, right? That's how this line emerged, right? This line didn't come, it was not there initially, right? Initially, we started with the random line. We have something called as training phase, right? So this line is the thing that we have optimized, or this line is the thing that we have optimized in SVMs. In the case of logistic and linear regression, we have certain loss functions that we have already discussed in the previous sessions, right? And that's why we say it's. But what in the case of KNN, what do we optimize? We don't optimize anything. And that's why it's called lazy. It's lazy, and it's non-parametric. Now, what do you mean by non-parametric? Well, it essentially, in the case when I'm training something, when I'm training a model, that training is dependent, or the optimization is dependent on the features, right? It's dependent upon the features of the samples that we have collected in the training data set, right? It's dependent upon the features. So when a new data point comes, we initially analyze its features. In this case, the y-axis value and x-axis value, feature 1 and feature 2, and then calculate its relative position with respect to the, use its features to calculate its relative position with respect to the decision boundary. But in this case, in the KNN algorithm, it's ignorant about its features. It's totally ignorant about its features. It just looks at who are my nearest neighbors, and then that's the only thing it's concerned about. It's totally ignorant about its features, and hence we can say it's non-parametric. Parameters are only required when we have features, right? But then how do we learn, right? How do we learn, as in how do we classify this point? How did we classify this point? We looked at its nearest, we measure the distance of this point from every other possible point that we have in the initial data set, and then we compare and reach a conclusion. That's why we have the third jargon here. It's called instance-based learning. We do this thing every time we have a new data point in the new data set, right? And that's all. So these are all things that I've already covered, that you already know from my previous discussion, but I just discussed it once again because these are terms that you're likely to see in the future, right? When you read articles regarding KNN. Now, how do you find the optimal value of K, right? So that seems to be the only parameter here, K. So, and that indeed is the hardest part of building a KNN model. So as a rule of thumb, if you are in a hurry, and then you can choose K as square root of n, right? N is the number of data points in the initial data set, in the training data set, or the initial data set that we actually have, right? So just take the square root of n and set K is equal to square root of n. Okay, it's likely to give correct results, but the best way is to make a graph between loss and K and choose the correct K value with the least loss or the highest accuracy, and then we choose that particular value for the implementation of the model. I will explain about this when we move to the code implementation. Okay, right? And distance, right? Distance is a term that shouldn't confuse you, but after seeing this slide, you might be confused, right? What on earth is this thing, right? It seems to be very abstract, you know. There's some p here, and you haven't seen this distance, right? And it's called a weird name, Minkowski distance, and so on. But it's not weird. The distance that you know, or the distances that you know, Euclidean distance and so on. Euclidean distance and Manhattan distance are special case of the Minkowski distance. So if we set p is equal to 2, we get the Euclidean distance or the Pythagorean distance. This is something that you already know. And Manhattan distance. So just to discuss these two, I will take an example of a 3, 4, 5 triangle. In the case of a 3, 4, 5 triangle, okay, so this is a 3, 4, 5 triangle right around here. So here we can go 3 to the right, 4 to the top to reach from one edge of the hypotenuse to the other edge, or we can directly climb along the hypotenuse, right? So suppose I am in a street, right? In a street you can't directly go across these buildings, you can only go straight, and then you can only go along the roads, right? And Manhattan, a city in America, had similar city architecture in which you could only go straight you could only go straight. So you can go, so if you need to move from point A, from one edge of the hypotenuse to the other edge, you need to go along these roads, right? So 3 to the right and 4 to the top. So the Manhattan distance would be 3 plus 4, 7. My Euclidean distance is 3 square plus 4 squares under root, which is 5, right? And P, and most of the time we use Euclidean distance, right? That's the most sensible, I would say, distance to use. But we can tune P also. P can also be considered as a parameter in this algorithm. But the major parameter that we are dealing with is K, right? Limitations of KNN, time complexity and space complexity. Right, these are terms. It takes a lot of space. It takes a lot of time. That's it. Okay. Again, you don't need to be intimidated by these two terms. So, what do you mean by space complexity? It really refers. Like how did we classify a point here? We took the distances of a particular point. We collected all the distances of a particular point from all the points that we have in the initial data set, right? And then we arrange them in ascending order, and then we chose a value of K, and based on the chosen value of K, we take a majority decision among the topmost values that appear in that particular data frame, right? And here we have to measure the distance of a point from all the possible points that are available in the data set, right? And this takes, and then we need to store it, right? Then we need to store this thing in the computer, and that's why it takes a lot of space, and that's why it's space complex, right? And what do we mean by time complexity? You should have heard about these two terms if you have indulged in programming, and I believe you have. And especially in CP contests, these terms come up frequently, right? And time complexity essentially refers that KNN algorithms requires a lot of time to complete. It also refers to one more thing, right? So one thing that increases the space or the time complexity is this thing. That's the number of data points that we have, right? So initially, if we had 10 points in the initial data set, we have to, when a new data point comes, we have to measure the distance of that particular data point from all those 10 points, right? And if we have 100, we have to measure the distance of that particular point from all the 100. So that's one thing that increases. Another thing that increases the time and the space complexity would be the number of dimensions, right? In the two-dimensional feature space, we only had two variables that we need to be concerned about, right? The x coordinate and the y coordinate of a data point. But what in 3 dimensions, the number of dimensions increases to 3. So we need to take account of 3 variables. In 4 dimensions, similarly, it scales up. So the time and the space complexity varies in proportion to the number of dimensions as well. Okay, so if you double the number of dimensions, the time taken to execute the program will be doubled. If you double the number of data points that we have in the initial data set, the time it takes to run the program would be also doubled, or run the algorithm would be doubled. Again, those guys who have joined the session late can again take up this scan this QR code and register their attendance. You don't want to miss your certificates, right? And so I will give you 30 seconds. Yeah, so I think we'll now move to naive-Bayes algorithm. So KNN is completed. I have a code implementation. I think I will show it after doing naive-Bayes also. Or I think it will be difficult to navigate between the tabs. So after showing naive-Bayes algorithm, I will show the code implementation of both KNN and naive-Bayes. Okay. And I will handle doubts later. If you have any doubts, reserve them for the end of the session. I will be asking them at the end of the session. Okay, fine. Now let's move to naive Bayes algorithm. And we will have a, so we won't be having triangles and circles here. We will be having something else. Okay. So say suppose we want to classify emails, right? Emails are something that we receive regularly. And if we want to classify emails as spams or normal messages, right? So we have an algorithm in Gmail which automatically classifies all the incoming emails as either spams or normal messages, right? And it removes a large amount of messages that we are to receive, right? And we will do this, okay, and we will have a simple classification scheme on the basis of presence of certain words. So the features that I am considering is the presence of certain words, right? Namely, dear, friend, lunch, and money, right? These 4 words: presence of the word dear, presence of the word friend, presence of the word lunch, and presence of the word money. So we collect all the messages that we initially have. Say we have 12 messages, of which 4 are spams and 8 are normal messages. And we go through each message, and if we will check if a particular word is present. That's dear is present, friend is present, lunch is present, money is present, right? And then we will make a frequency table or histogram or whatever way in which you want to represent the data. Okay, we need to have that data. Okay, so what we are trying to do is in this algorithm is this thing, that is, we are trying to figure out the probability of the message being a normal message given it has the words dear and friend. That is, we received a new message and the new message consists of the words dear and friend. Okay, or say the message is dear friend. How likely is the message to be normal? How likely is the message to be spam? And which argument or which supposition is stronger? If the former supposition is stronger, then we'll classify it under normal message. If the later supposition is stronger, we'll classify it under as a spam, under the label of spam, right? Right. So this term in red is the term that we actually want, right? Probability that message being a spam given it consists of dear friend. This is our objective. We are on a hunt for a treasure, and this is the treasure that we are hunting for. So never forget this thing, this term. Okay, probability that message being a spam given it consists of dear friend, right? Now I'll just multiply with this thing, okay, times the probability of message consisting of dear friend. Okay, and that is equal to the probability of the message being a spam and consists of the phrase dear friend, right? Probability of message being a spam and consisting of the phrase dear friend. Note that these are 2 independent events, right? Message being a spam and consisting of dear friend. That can be rephrased in these 2 different manners, 2 distinct manners. That is the probability of the message being a spam given it consists of dear friend times the probability of the message consisting of dear friend, or the probability of the probability that the message is a spam times the probability that message consists of the phrase dear friend given it is a spam, right? I think this makes intuitive sense to you. There's no math involved here, okay? There's no math involved here. Say if the message is a spam and consists of a dear friend. Imagine a physical situation in your head. You have a spam and consists of the phrase dear friend. Now that can be equal. That situation is equivalent to a situation in which the message is a spam, and then I turn the message over and then I see the phrase dear friend, or I read the message first, which which consists of dear friend, and then I turn the message to see what it is, and then I see that it's a spam, right? So we want to know this term in red, right? For that we can compute this probability that message is a spam times the probability that message consists of the phrase dear friend given it is a spam. Okay, we are hunting for this thing here, and we can compute it using this thing here, right? Okay, and similarly we want the probability that message is a normal one given it consists of the phrase dear friend, right? This is the second thing that we are hunting for, and then we will compare the two and figure out which supposition or which argument is stronger, right? And then we'll base a classification based upon that, right? We'll do a classification based upon that. We have a similar argument here, so that when this thing is multiplied with the probability that message consists of the phrase dear friend, it becomes the probability of the message being a normal message and consisting of the phrase dear friend, which will be equal to the probability that the message is a normal message times the probability that message consists of the phrase dear friend given it is a normal message. Just try to think about this thing in your head. Okay, this is completely intuitive. There is no math here. This is just try to think. Okay, just try to think, just try to imagine it in your head visually, and then you will see that this makes perfect sense. There is no math here. Okay. Okay, and this is the thing that I was talking about, right? We make a histogram. Okay, and next few slides should be very clear to you, right? We compute the probabilities, right? So here dear, there are 8 messages, right? I mean there are 8 messages of which there are 8 normal messages of which all the 8 of them consist of the word dear, right? And similarly we have the tally marks or the frequency table or the histogram for all these things, right? For the word friend, for the word lunch, for the word money, and in the case of spam as well, we have a similar histogram, right? So remember what, in order to hunt for this thing, we just have to figure out the probability that message is a spam times the probability that message consists of the phrase dear friend. The probability that message is a normal message times the probability that message consists of the phrase dear friend given it is a normal message. So this is something that we can have from here. What's the probability that it's a spam? It's 0.33. Why? Because there are four spams and there are 8 normal messages. Of the 12 messages that we initially have, 4 of them are spams. So 4 by 12, 1 by 3. Subsequently, 2 by 3 is the probability of the message being a normal one, right? And similarly, from this histogram, we can actually say that, say if the message is a normal message, what's the probability that it consists of the word dear? It's 1. It's 100%, because in all the normal messages, we can see the word dear, right? Similarly, we can evaluate the conditional probabilities. Okay, it's referred to as the conditional probability because we are basing ourselves on a particular condition. Given it is a spam, given it is a normal message, and so on. Right? This is how we represent a conditional probability. So this refers to given probability that message consists of the word dear, given its normal message, right? Now this is already now in order to evaluate the left hand side, right, this thing here, we just need to evaluate this thing here, right? Probability that message is a normal message times the probability that message consists of the phrase friend, right? And that's what we are doing here. Probability that's a normal message times the probability that's it consists of the word dear given its normal message times the probability that consists of the word friend given its normal message. Of course, we wanted to figure out the probability that the message consists of the phrase dear friend, which can be further split into 2, dear and friend. That's what we are doing here. Dear given n times the probability of friend given n. And we do the same thing for spams as well. So the first one, and sometimes you might think that we ignore this term here. Probability that message consists of the phrase dear friend. And and I know that all of you are smart enough to understand that this term is, we can ignore this term because we only need to compare these two things, right? The things in red, the terms that are being highlighted in red. And for that, I am only comparing these terms, right? The bottommost terms in the two slides. Because here we are multiplying with a common term, right? For both calculations, it's the same term, the probability of the message consisting of the phrase "dear friend." Here also, it's the probability that the message consists of the phrase "dear friend." So it doesn't really matter because we are just comparing the values. Okay, we are just comparing the values, and hence it doesn't really matter. The comparison scheme. Of course, this is not the probability, but it will be proportional to the probabilities, and we can safely compare the two values. So, dear friend is more likely to be a normal message than it is likely to be a spam, right? Hence, we know that the first argument is stronger, and hence we can say that the message that we have received with the phrase "dear friend" is a normal one. And hence, Bayes' theorem, right? As this is one of the most, this is the most important formula in all of probabilities. It's a very intuitive one, right? This is something I will explain it to you, but this is something that you have to realize within yourselves. Okay, it's something that you can, as Galileo once stated, the greatest truths about nature cannot be explained or taught. It has to be realized within oneself, right? And Bayes' theorem is one of those things which you can intuitively derive it. Okay, and if you were attentive enough, you have already derived it because that's what we did in the example, right? But we'll just do it once again. This time I will go a little bit fast. Okay, probability of A and B happening is the probability of A happening provided B happened times the probability of B happening, and we can rephrase it in another way: probability of B happening provided A happened times the probability of A happening. And we have this term here, the first expression here and the second expression here, and we can equate the two expressions, right? Probability of A happening provided B happened times the probability of B happening is equal to the probability of B happening provided A happened times the probability of A happening. And don't confuse that B causes A or A. There is no element of causality here. B doesn't cause A, or neither does A cause B. Okay, it's just a way in which we can phrase things. And this is Bayes' theorem actually. This is not the Bayes' theorem that you have learned in 12th standard, right? So for brevity, I'll just condense all the verbal explanations that are given in the earlier slide to mathematical symbols. And now you have this thing here. This thing here is the Bayes' theorem that you might have studied in your 12th standard, right? And that you have repeatedly used to solve all the exercises. But I think most of you might not have realized what it really means, and some of you might have. So for those who haven't, this is how it's all derived. Okay, it's pure intuition. Bayes' theorem is pure intuition, but it's tricky, right? It's kind of hard to wrap our mind around this thing, but it's pure intuition, right? And so the features that we took, right? So one feature that we took was the presence of the word dear, right? So presence of a particular word. That's the feature that we used to classify the messages. Now, presence of a particular word can only take two possible values: yes or no. Okay, yes or no. So this is called multinomial Bayesian classification, in which it can only take discrete number of values. Okay, in this case too, so we can also call this as a binomial classifier, binomial Bayesian classifier. Okay, if there's three trinomial Bayesian classifier, say, and if you have multiple, then we can, so if you have n number of discrete examples, discrete values that a particular feature can take, then it's called as multinomial Bayesian classifier. But what if we had a feature? What if we had a feature that took continuous values? Okay, instead of discrete values, it took continuous values and an infinite number of values, a continuous and infinite number of values, right? And so in the email classification example, I will add one more feature, that is the number of words. Okay, and spams tend to, I am assuming that spams tend, this is my own data set, okay, and I am assuming that spams tend to be shorter and normal messages tend to be longer, right? And now we have a new problem. We get a new message which has the words dear 20 money 43. The numbers in the bracket signify the number of times that particular word has repeated, which means dear 20 times, money 43 times. Okay, so dear money, so on. So this is the message, this is the phrase that we have obtained, and we need to, in the message, and we need to classify if the message is a spam or a normal one. So we now in the calculations, you thoroughly remember the calculations. I know you do, you are listening very attentively. So now we need to include one more factor into calculations. We need to include one more factor into calculations. It's the probability that message has 63 words given it is a normal message, and the probability that message has 63 words given it is a spam. So to enlighten you a bit, right? This is the calculation. This is the complete calculation. Probability that message is a spam times the probability that message consists of 63 words given it is a spam times the probability that message consists of the word or the phrase, should be phrase, okay, phrase dear 20 money 43, and this thing, the same thing for the normal case, in the case of a normal message, right? We have this additional factor. So now our goal has changed. Now how do we figure out this probability? The probability that message consists of 63 words given it is a spam. The probability that message consists of 63 words given it is a spam. And the probability that message consists of 63 words given it is a normal message, right? How do we go about finding those values? So this is our goal. Okay, this is our goal. Don't forget our goal. But we see that in the initial data set or initial data set where we have accumulated, that we have collected, there is no data available for letters that are 63 words long, right? I don't have any letter which consists of 63 words, but we cannot expect that, right? We cannot expect that because we can't expect for us to have to have a large number of messages which consist of all possible values that the number of words can take, right? I mean, it's very unreasonable. It's irrational for us to expect that we have all the messages. We have messages which consists of all possible number of words. I have a message with 90 words. I have a message with 91 words. I have a message with 92 words. It's simply not possible. And so what do we do, right? We are in a dilemma. But okay, now I know that you are familiar with these two terms, mean value and standard deviation, right? One standard deviation refers to the variability of that particular data, right? And mean means average, right? So that's something that we can calculate from the data from the data we have, and we calculate these two values. So why the mean and the standard deviation? They capture the essence, right? They effectively capture the essence of the data that we had, right? So these two are very famous very common statistical measures that we use. Now I am going to introduce you to a formula from the back of the curtain. Okay, don't be intimidated. It's this formula. Okay, this formula. You might have seen this formula, you might not have seen this formula, but this formula, if you plug in, okay, just look at the formula, just don't think anything and just plug in the values of sigma and mu into this formula, right? And plot the graphs. After plotting the graphs, I will say anything more. We get these two very beautiful graphs, right? It looks so symmetric. It looks so satisfying, right? The graphs, right? And so what's the formula? F of x is is equal to 1 by sigma times root 2 pi e raised to minus 1 by 2 x minus mu minus sigma divided by sigma the whole square. Right? What is x? What is f of x? Or what is y? Right? F of x is y. What is y? What is x? So x refers to the number of words. Remember, what is our aim? Our aim is to find the probability that message has 63 words given it's a spam. The probability that the message consists of 63 words given its normal message. These are the two probabilities that we need to figure out, right? And this thing refers to as the conditional probability that the message consists of x number of words, given it's a spam. And the bottom graph refers to the value in the y-axis represents the conditional probability that message has x words given it is a normal message, right? And then you might ask, right, why? I mean, why should it, right? Why should it? Well, we are just assuming. Okay, this is basically an assumption. We think that the conditional probability that a message consists of x number of words, given it is of a particular type, should follow this type of distribution. This type of distribution that is mathematically given by this expression, right? It's called the Gaussian expression or the normal distribution. And this curve is what we call as the bell curve. And why should we assume that? Well, we don't know, right? So ranging in a large number of domains in physics, chemistry, and sociology, biology, molecular sciences, we see this distribution, right? From the distribution of stars in the galaxies to the distribution of IQ scores among population. So we see the same distribution in nature. So we think this is the most famous distribution in statistics, and it's called the Gaussian distribution, given by this formula. Okay. So what was our goal? The probability that message has 63 words given it's a spam. So we try to figure out 63 here, and then we figure out the y value, and that is the probability that message has 63 words given it's a spam. And then we reached our goal, right? This term was what we were hunting for, and we got that. And then we will plug into the old formula, and then we do the comparison as usual and reach to a conclusion. Right. Now we will have a short poll. So if you were listening attentively, I told you that the thing in the y-axis represents the probability that message has x words given it is a spam. The message has x words given it is a normal message, right? And now I want you to figure out the area of this graph. Okay, I don't want you to integrate the old expression. It will take you weeks to do that, but I want you to figure out the area of this graph, okay, just by pure intuition, because you know what the y-axis value represents. It represents the probability or the likelihood that message has x words given it is a spam, right? So I will conduct the poll here. I will give you the, yeah, right. This is the QR code, okay? I will, right? This is the QR code. So I will show this for 15 seconds and I will show the other screen, which also consists of the QR code. So you don't need to worry. Right. So I will give you 30 seconds, 40 seconds, and just give me the area of the graph. Okay. So I think we'll show the results, right? Yes, 71%, right? So 71% has said the area of the graph is 1, and it's actually true. Okay, it's true that it's 1. Okay, and infinity 8%, area could be anything 5%, right? Yeah, it's all reasonable. Okay, they are all reasonable estimates, but the area of the graph is 1. Okay, and why should it be 1? Why should it be 1? It's interesting. Why should it be 1? Well, it should be 1 because what do we mean by the area of the graph in this case? What's the meaning of that, right? And it's from that meaning that we can reach the conclusion that the area of the graph is 1, right? So the y-axis represents the likelihood, right? It represents the likelihood or the probability that messages 63 words, messages X number of words given it's a spam, given X number of words given it is a spam, right? And so a message. So I have a message now. I know that I'm guaranteed, I have 100% probability that the message that I am going to read is going to consist of some number of words, either 2 words, 3 words, 4 words, 5 words, or maybe 1,000 words, 2,000 words, whatever, right? And I can add all those bits of probabilities. So the y value, this strip around here denotes the chance or the likelihood that what's the chance that the message, say if the message consists of 40 words, right? In this case, right? 40. Say the message consists of 40 words. What's the probability that the message consists of 40 words given it's a spam? This is 41, 42, 43. And so if we add all the likelihoods, if we add all the probabilities, we are basically saying what's the probability that messages any number of words. It messages any number of words, 1 word or 2 word or 3 word given it's a spam. And it has to consist of some number of words because it's a message, right? It's after all a message. So the probability is going to be 1 or is going to be added up to 1. Of course, you can reach the same conclusion if you integrate it, but yes, it would take you a lot of time, right? And one last time, okay? So some of you might still have some trouble registering your attendance. So I will show this this QR code for 30 seconds, and then we'll move to the code implementation. And if I have time, I will cover some more topics regarding this thing. But now you are all set to understand the code behind KNN and Gaussian and naive-Bayes algorithm, right? Right, guys? I think all of you guys have registered your attendance here, and now we'll move on to the code implementation, right? So you can see the code, right? Guys, can somebody, Rutik, can you, Rutik or Rishi? Yeah, fine. So we'll start with KNN, and then we'll move on to the naive-Bayes algorithm, right? And before moving on to the code, I would like to say that I won't be explaining each and every line of the code, including the syntax, right? I will be explaining the code block-wise. I think that's much more reasonable way to do, because if you want to learn to code, then you have to practice it on your own, right? It would be like learning how to drive, sitting on the passenger seat and listening to the talks of the driver while he's driving, right? So you have to kick the driver out of the driving seat and drive the car if you need to learn how to drive, right? And similar is in the case of coding. It's relatively simple, but you need to, in order for you to learn it, you have to actually feel the code. You have to actually run the code, to type the code and run it. But I will be explaining as best as I can, and I think I will be doing a decent job in that, right? So in the case of KNN, this is something that Rishi had done. Let's import the necessary libraries required, right? First, you need to import the necessary libraries, right? These are the 3 libraries that you might be well familiar with after the first session, right? Pandas, Matplotlib, and NumPy. And this is again something that you might be familiar with, scikit-learn, right? You import the datasets. I'm using the same dataset as Rishi's, so IRIS dataset. So I don't need to explain much on what it consists of, right? Anyway, I will show you what it consists of anyway. It consists of the sepal length, sepal width, petal length, petal width. 4 features, right? We are considering 4 features. So the feature space is going to be 4-dimensional, okay? So it's not something that you can visualize in your head. And target means it actually refers to the labels, okay? We have encoded this as zeros and ones and twos because we can only deal with numerical data, right? So 0 refers to one particular species, 1 refers to another particular species, and 2 refers to another particular species, right? And then we'll be splitting the data set. I think I need to zoom in a little bit, right? Then we'll split the data set into 2, right? Into the target data set and into the feature data set, right? So from this data set, if we drop this, right? If we just cut this thing off, that's what A and that's what B is. And this is defining the mean score scale distance. Again, this is not something that I should be explaining in detail because I have given you the formula of mean score scale distance and just coding this thing. For hard coding this formula, that's code. And again, this is a very famous thing, very famous, syntax that you should be familiar with, right? Because in any model, when we always split into training and testing data set, right? We always split a given available data set into train and test. And that's exactly what we do here as well, right? And so test size is 0.25. So we have this initial data set, which consists of 150, right? 150 samples. And 1/4 of those samples, around 38 samples, will be allotted to the testing data set, and 75% of it would be given to the training data set, right? And then we'll split it. And this is the crux of the code, right? This is a from scratch implementation, by the way, right? Again, this is the KNN functionality, okay? So again, I will explain the algorithm once again. So what do we do? For each point that we have in the new data set, in which we have to predict the labels of the classes, we take 1 point at a time. That's what this for loop signifies. We take 1 point at a time. And then we take each one of its features, right? Each one of its features represents a dimensionality in the 4-dimensional feature space, right? That's the x coordinate, y coordinate, z coordinate, and the w coordinate, right? And then we measure the distance. We measure the distances of that particular point from all the 75% of 150. What's that? 75 points that we initially have, right? In the training data set, that we are giving for training, and then we are going to append it to this thing, distanc, okay, distanc, which consists of a list of all the distances. And then we convert into a data frame because we have a lot of functionalities that we can deal with data frame. It's currently an array, right? We are converting into a data frame, and then we are doing some sort of re-indexing here, just for the sake of for the code to smoothly run. We are just re-indexing the thing, okay? And then we are sorting it, because why do we need to sort it? Because now the distances are in random order. We need to know the smallest k values, right? Smallest k values, the k nearest neighbors, right? And that's what we are doing here, sort it, and then tab.head. Head is a very famous functionality that you can use for data frames. It prints the top k values depending upon the argument of it. So the argument of the head is going to be k, right? And then then we have to take the majority vote decision. So this is the code this is the portion of the code that takes the majority vote decision, and whatever the majority vote decision is, the label is appended to that, right? And that's it for one, right? That's it for one new sample point that we are trying to classify. Now in the testing data set, or whatever data set in which we have to predict the in which we need to predict the labels of each of the points in the new data set, we have to analyze all the points, right? That's why this for loop was for, remember? So we go by we iterate row by row by row, and append, for each row we will append the predicted class in y_mtest. I hope it's clear. Then again, this is a famous functionality that you must be well accustomed with if you are seriously gonna pursue ML. Right, from scikit-learn metrics, you import accuracy score. So this is just, right? So we already have y_test, right? We have we have y_test from initially, right? We have y_test, and right, the y_test we pass into, that's the first argument that we pass into accuracy score, and then second one is y_mtest. What does the algorithm predict? And we see that we can see a remarkably they are concurrent, right? To an extent of 97% or 0.97. So this is the predicted class. Okay, this is how the algorithm predicts that the first data point is going to, the first sample that's going to be in the testing data set is being classified under the label of 0, the next one 1, and so on, right? And next time you need to implement KNN, you don't need to sweat it all over, right? Implementing it from scratch. You have an inbuilt function. We never use from scratch implementations, but to get an idea of what we are doing. That's why we are implementing from scratch. Now, the inbuilt function, this is something that you need to be well familiar with. One is k-neighbors classifier, and then you just pass the arguments. It's very easy. You just pass the arguments and then you just print it, and it's again the same accuracy, and it should be, right? And it should be because it's the same thing that we are doing in the inbuilt function and in the from scratch implementation, right? And I promised you that I will try to find out the optimum value of k, right? I chose k as 5, right? You can choose any value of k, and the best way to figure that out is to plot a graph between accuracy and k. So here you can actually see that the graph, this is the graph, okay? So what I'm doing is that I'm trying, like here the accuracy was 97%, right? Now in this block of the code, what I'm doing is that I'm varying this value of k, and then accuracy also varies, and that accuracies are going to be appended into an array, and then we are plotting it, right? And you can see that for k around 0, it's supposed to be a very low accuracy, but for some reason this plot doesn't show that. It's supposed to be very inaccurate when k is near 0. But as k goes from 0 to 5, 4, 5, and when k tends to be in this middle range of values, it's supposed to show, and it is showing very high accuracy, like around here, right? Around here, it's around 5, okay? Right, it's not easy to scale, but you can see that it's around 5. It's near close to 0. So if this much is 20, this much would be around 5. Right? And as the value of k increases, the accuracy drops, right? And now naive Bayes, right? Wait. Right, again, we are importing the necessary libraries, right? We are using the pre-processed data, and this is the data we initially have, right? I have for Brady, I have excluded target is equal to 2. We are just dealing with two classes. Right? There is one class in which one label in which target becomes 0, and another label in which target becomes 1, right? The target is equal to 2 is omitted from this data frame. and we further split it into two, right? One which consists all the information of separating all the features, in which output spits out target is equal to 0, and all the features, the values of all the features which spits out target is equal to 1. That's what we are doing here. And then this is a functionality that you would like to have in your arsenal, right? df.describe, right? When you do that, you get all the information, you get all the statistical information that you need for that data frame series wise in the sense column wise, right? So you get the mean, and we are only interested in the mean and the standard deviation, remember, because this is a Gaussian situation, right? Because the data values are continuous. Sepal length, sepal width, petal width are continuous. So we are employing Gaussian neighbors classification here. And here, again, right, sepal length, right, we only need the mean and the standard deviation. We have all the necessary statistical measures, but we only need mean and standard deviation, right? And this is for target 0, okay, df1. I told you that I split it, right? So df1. And right, from this mean and standard deviation, we are further accessing, splitting. We are just accessing these two rows because these are the only two rows that we require, right? Mean and standard deviation for each column in the data frame. And so that's what we are doing, mean here and standard deviation here. And then this is the mathematical function. This is the mathematical function that I introduced, e raised to something, right? E raised to x minus sigma by mu the whole square, right? And we are materializing that equation here. And then, right, again, this is the crux, or this is the major portion of the Gaussian algorithm or the Gaussian classifier, right? So we are using a for loop here. Again, we are going row by row, right? For each row, we will have a result in the test data set, right? We will have a result in the sense we will classify it under some label. So initially we start with probabilities being 1, because we need, remember, we need to multiply each of these probabilities, right? We need to multiply a range of an array of a continuum of conditional probabilities. So for that, we'll use for loop iteration, and hence we need to start with p1 is equal to 1 and p2 is equal to 1. And then we'll go again and again in this for loop, and then we'll multiply each of the conditional probabilities, which is given by the Gaussian value. You remember that, right? And the Gaussian value in the sense, the thing that this functionality spits out when we feed in the standard deviation, mean, and x. So it will give the probability that it consists of x number of things given it's of a particular type. The probability that that particular feature is x given it's of that particular type, right? And then, right, then we are comparing the probabilities, right? You know the algorithm. And if it's p1 that's larger, it's going to be 0. And if it's p2 that's going to be larger, it's going to be 1. And this is it. And this is very interesting. Like naive Bayes gives an accuracy of 100%, right? 100%. Okay, you can't expect that in every time, but since this is a small model, in this case, gives you 100% accuracy. So we know that KNN gave you 97% accuracy, while naive Bayes gives you 100% accuracy. So it's a very effective way in which we can classify things, right? Of course, you can't expect this every time, but still, it's way more than KNN. Okay, not way more than, but better than KNN. And right, again, this is the inbuilt function. That was a from scratch implementation. This is an inbuilt function. This is an inbuilt function, right? Again, it's giving the same accuracy, and it should, because we are doing the same thing in both cases, right? And yes, I know it's 7:41. Some of you might be tired, right? And this is it, guys. I think we can wrap up here. And if you have any doubts,
I guess you can once again show the QR code for attendance, because many of them are requesting for that. And then you can take up any doubts at the end, and then we can wrap up.
Yeah, fine. So this is the QR code that you need to register your attendance. So So if any of you guys are still left to register your attendance, please scan this QR code. Right, I think all of you guys have registered your attendance, right? Yes, and I think I can take up some doubts now, and I think you should be having some certain doubts. I don't think I have explained everything clearly. So, right, you just have to raise your hand, or we will allow everyone to unmute or something.
Yeah, what I'll do is whoever is raising the hands, I'll be enabling the mic for them so that they can speak.
Yeah, fine.
Yeah, go ahead, guys. Everyone, whoever has raised their mic, raised their hand, have unmuted, have enabled the mic access, so you can unmute and speak.
What should P be in the distance?
Yeah, what should P be in the distance? Yeah, that's a very good question. Like when P is equal to 2, right? I will show you the formula first. Right. So this is the formula, right? Right, that you're talking about. So in this case, when P can be anything, right? P can be anything. P is a parameter that P is also a parameter that you can tune, just like K. But most of the situations, in most of the cases, we consider the Euclidean distance. In the case of Euclidean distance or the Pythagorean distance, we have P is equal to 2. But it's always wise for you to change the value of P and then just like as we did in the case of K, we plot a graph between accuracy and P and vary the value of P and check which P gives you the best answer, right? And in most of the cases, P is equal to 2. In the case of P is equal to 2 case, it's called the Euclidean distance, the well-known distance formula that you all are accustomed with. And yeah, P could be literally anything. P could be anything, but it's in most of the models, P is likely to be, P is equal to 2. Okay, we consider the Euclidean distance, right?
Hello?
Yes.
During the base theory thing, you said it is not
Yes.
the same as the 12th class thing, right?
I'm sorry, I couldn't hear. Can you repeat the question?
You said it is not the same thing as we learned in 12th class.
No, it's the exact same thing that we learned in 12th class, but here we are using it for classify. No, I think you got me wrong. The thing is that in the case of 12th standard, you are just introduced to a formula and then you grind that formula to solve all the problems that is available in the back of your text. So, but you need not do that. It's something that's much more intuitive. Okay, it's the same thing. And I was trying to take you in an intuitive walkthrough. Okay, that was what I was trying to do. It's the same
you're saying that it's not the way to follow the formula, right?
Yeah, exactly. Because the whole purpose of this thing, yeah.
Fine. Any other doubts? You can still unmute and you can speak up. And also adding to that, where you can check all the content material has been uploaded on our GitHub page, and the link also has been shared on the WhatsApp groups. We'll be sharing it again. So in order to check the material, the collab notebooks, the CSV files, you can find all of these on the GitHub page itself. Okay. And also, as told earlier, we'll be sharing a mini quiz at the end. After the session ends, we'll be sharing all the relevant content. We'll be sharing the GitHub link, and also along with that, we'll be sharing a small mini quiz which you guys can try out. I guess that's all. Since there are no other doubts, so you can wrap up. Thank you all for joining. See you in the next session. Yeah, thank you.